All right, so now let's talk about some sort of technical bits of this stuff. All right, so this is going to look like a lot of theory and definitions and stuff, but, well, they're important, so we need to talk about them. Right? So we can say, remember when we first talked about line integrals, we were saying that, yeah, line integrals really do depend on the path of integration. Right? That was one of the first examples we did. Well, so there's a terminology for when they don't. Right? So we say that a line integral, let's call it f dot dr here, is independent of path right? Independent of path if given any two curves let's say C1, C2, which start and end at the same point, well, at the same points. So they both start at the same point and they both end at the same point. So if they both start and end at the same points, then the integral along C1 equals the integral along C2. All right? So, right, that's what it means for a line integral to be independent of path. All right, so we just talked about the fundamental theorem of line integrals, and that tells us, so fundamental theorem of line integrals says that line integrals of conservative vector fields so I'll just abbreviate that. Conservative vector fields are independent of path. Okay? Well, now you could ask, is it only conservative vector fields that are independent of path? Well, we'll get on to that in a second. First, we need some definitions, though, right? So what does it mean for a path to be closed? So we say a curve C is closed if it starts and ends at the same point. Okay, so something that is closed is, think of like a circle, right? So things that are closed, maybe this squiggly dude, a circle, a square, right? Things that are not closed would be a half circle, this wavy line here, something that kind of does that, right? It actually has to close up, all right? Okay. So we'll continue this and, well, let's erase the screen and then continue. We have this there. if the line integral here, f dot dr, is independent of path in some region D if and only if its integral around any closed path in D is 0. Right? Now this actually isn't so challenging to prove, so I want to challenge you. Prove this theorem. You can do it. It's not so bad. Basically, let me say the idea is to show that independence of path implies that the line integral around any closed path is 0. You kind of just want to split the closed path into two pieces, into two paths from A to B, right? Where A and B are 2 points you've chosen on the closed path. The other direction, you start by saying, okay, here are any two paths between a point A and a point B. You can stick them together and make a closed path. So then you know the integral around that should be 0. Right? So that's a little sketch of the ideas of what to do. Try on your own to put those together and actually get a proof of this theorem. Right? You can actually do it. It's not too bad. All right. But what we really want to get at is a way to tell whether a vector field is conservative or not. So how do we do that? Well, we need some definitions. Right? So D here, this D, this is going to be a region in R2, or it could be in R3 as well. Okay? So we say a set D, or a region D, is open if every point P in D has sort of a disk or a ball that you can draw around it that's contained entirely in D. All right, so kind of what are some examples for 2D that looks like? So an example of an open thing would be, say, a disk with no boundary, or, oops, or a square with no boundary. Basically things that don't have any boundary whatsoever, right? Or have none of its boundary points. Now what's something that's not open? Well, the closed disk, right? Where it's everything. So of course these are filled in too, right? But so a disk with its boundary, that's not open, because if you take a point on the boundary, well, any circle you draw around it leaves the disk. Likewise, I can take a square, or in this, well, it looks more like a rectangle here, where I've actually included two of its edges, right? Then I'm fine over here, but on these edges I have that same problem, right? So I want to just point out the opposite of open isn't actually closed. So this is an example of a closed thing. This is something that's neither open nor closed, right? In the sense of what this open means. Okay? All right. Then we can talk about a region or set being connected, right? What that means is if you have 2 points in that set, then there's some way to walk from point A to point B without ever leaving the set D, right? And you know, that path that you walk along, you can consider just kind of drawing out that path in the region, and that's what it's talking about here, right? Okay, so now that we have all this stuff, we can talk about this. Right? So suppose F is a vector field which is continuous on an open and connected set D. So this is an example of something open and connected. Something not open and or say open but not connected. You could imagine taking both of these together and calling it D. So you have an open disk over here somewhere, and you have an open square over here somewhere, right? And if you're saying that's D, then that's not connected. It's open, but it's not connected. Okay. So if you have an open connected set, if the line integral is independent of path in D, then it's conservative. Then F is conservative. Right? But, so this is a great theorem, because now we have some way to describe what it means for it to be conservative. The problem is, this condition here, showing that a line integral is independent of path, that can get really hard. So we want to ask about, well, is there a better way to do it? Well, we'll talk about that in a bit.